Okay, now we're going to talk about put-call parity. So put-call parity represents a relationship between put and call prices. The price of a call minus the price of a put is equal to the price of the stock minus the strike price, the present value of the strike price in continuous time. For our purposes, we're not going to use continuous compounding. This formula is for reference only. For our purposes, the next formula, and I'll actually rewrite it for you. This is an extension for European call options on dividend-paying stocks. In this case, the price of a put is equal to a call minus the stock price plus the present value of the strike plus the present value of dividends. In our case, we're going to be assuming non-dividend paying stocks, so you can strike the present value of dividends. So for a call, rewrite it. It's equal to the put plus the stock price minus the present value of X. I believe I wrote that correctly. So if you're looking at put call parity, the price of a call has to be equal to the price of the put plus the stock price minus the present value of the strike. Again, these would be a call and a put with the same strike price. So if this is not the case, then an opportunity for arbitrage exists. We can recreate this position by comparing a long call and a short put. Okay, so we're buying the call and we're writing a put. So basically, this is identical to the leverage equity position that we created in our with our binomial option pricing model. So what we did with leverage equity, we created a position where the strike price was our reference point for our profit or loss, and that's the same situation you can create if you write a put and buy a call with the same strike price. This is an example of an arbitrage strategy where you buy the stock. So in this case, we're buying the stock at 110. It's the strike is 105. We borrow the strike price. In this case, it's continuous compounding. So that's we multiply the strike price by the exponential to the power of the risk-free rate multiplied by time. We sell the call. In this case, you get $14 for the call, and you buy the put and you pay $15 or $5. So as a result, you net out $1.41. Again, this is an arbitrage example, not a real world example, but is a potential example that might occur if put call parity did not hold. So for reference here, put option valuation, the value of put option, the Black-Scholes formula, using continuous compounding, the value of the put option is the strike price. Again, we use either exponential to the power of the risk-free rate multiplied by time to expiration. And because we're on the other side of the trade, the put option, we have 1 minus the probability of normal random draw is less than D. So minus the stock price, again, the exponential minus the dividend yield multiplied by time, again 1 minus so because we're on the other side of that distribution. So in this case, the lower this value, the lower the value of D, the more likely we are to be in the money. So hedge ratios and the Black-Scholes model. So hedge ratio, or delta, is the number of shares to hedge price risk of holding one option. Option elasticity is simply the percentage increase in option value given a 1% increase in the value of the underlying security. So this figure 16.7 gives you an idea of what call option value and the relationship of hedge ratio. So the hedge ratio is going to be lower when we're down here than it is up here because of the slope. So if we were down here, the hedge ratio would be even less. So all that tells us, this tells us that as the value of the stock goes up, the hedge ratio goes up. So the higher the hedge ratio, the greater a number of shares that you would need to hold to hedge the ratio of holding one option.